The subject of how to create a randomization distribution gets pretty involved, and one of the reasons it gets so complicated is that the process is really different for each type of statistic that you might be trying to generate a distribution for. With Bootstrap, once you understand it for one statistic, you pretty much understand the process for all of them because the process doesn't really change. So our objective in understanding randomization distributions is not to fully understand how each type is generated, but at least to understand what some of the differences are between a randomization distribution, which we would use for a hypothesis test, and a bootstrap distribution, which we would use just for a confidence interval. So if we take a look at this example here, our original sample is given, and this is two quantitative variables. So we see this with a scatter plot and a regression line drawn. A bootstrap sample, recall that the bootstrap sample is not going to have any points on it that aren't on the original, but that it may have a few missing because it might have duplicates of some of them. Like this point here is on the original, and we see that it did not show up in our bootstrap sample. In general, we expect to see that our original sample statistic is not going to be that far off from each bootstrap sample statistic, although we will occasionally get a few of the more extreme values. What becomes really interesting is comparing the bootstrap sample to a randomization sample. The way this particular randomization sample would be generated is by taking an X from one point in the original sample and a Y from another point. So these X and Y come from different ordered pairs. The idea is that under the null hypothesis, there's no association between X and Y anyway. So what we do to generate a distribution that's based on the null hypothesis is completely disassociate all of our X's from all of our Y's and create a pool of X's and a pool of Y's and draw randomly from those pools to generate points. What you can see about this distribution is that the sample statistic we're looking at now doesn't resemble the original sample at all, and in fact it's close to zero, right? This value happens to be negative, but it's close to zero because in a correlation, the null hypothesis is that the correlation is equal to zero. So what you'll tend to see with randomization samples is that there is some variation in this sample correlation, but that the variation is all centered around zero instead of being centered around our sample statistic. Aside from that, the rest of the process of creating a dot plot would be the same idea as what we see in a bootstrap distribution. We generate another randomization sample, calculate another sample statistic, and that sample statistic again is one dot in that dot plot. Now when we go to look at the resulting dot plots from generating 3,000 samples in this case from each of these scenarios, we can see that our randomization distribution is centered at the null parameter, which in this case is 0. Because the null hypothesis is that the correlation is equal to 0. And that our bootstrap distribution is centered closer to our sample statistic. So this is centered at 0.728. Which is close to our sample correlation, which we decided was equal to 0.74. We can also, while we're here, think about how each of these distributions would be used. A bootstrap distribution would be used to find a confidence interval. And it makes sense that the one we use to find a confidence interval is centered at the sample statistic, just like our confidence intervals tend to be closely centered at our sample statistic. So use this to find a confidence interval. For example, looking at this, we can see that the center 95% looks like maybe it's approximately between these two values, about 0.47 and 0.9. So maybe my 95% confidence interval would be something like that, 0.47 to 0.9, just eyeballing it in this case. The randomization distribution we would use to find a p-value. So if our sample statistic, like we said, was 0.74, that's going to hit right about here. That's our sample statistic R. My p-value is going to come from counting the dots that are more extreme than that value. This is a very small p-value, right? One dot out of 3,000 dots total. So that p-value, let's see, bring in our calculator, 1 divided by 3,000 is about 0.0003 repeating. And each of the dots in this randomization distribution is a sample correlation R from that randomization sample that we were looking at. Each of these dots in this bootstrap distribution is also a sample correlation R, but from a sample that's generated using that bootstrap technique where we are resampling from the sample. There is no null hypothesis in this context. There's no hypotheses at all related to a confidence interval. So it makes sense that the null parameter wouldn't be relevant.